Well, the aim of today's lecture is to find the model that connects the set points for the angle of our aircraft to the linear speed or the angular speed of our aircraft. Okay? So this will be done from experimental data. We will excite the system with some kind of input data. We will get the response of the system, so the output of the system of this input data, and then we will try to fit a model, a mathematical model that describes the relationship between the input and the output variables. Okay, that's what we call identification in opposition to modeling, because modeling will find the mathematical model of our system, but by means or from the physical laws. But today, we have not precise, specific physical laws. We have experimental data. When you find a model from experimental data, input, output, we call it identification. So that's the aim of today's lecture, how to find the model of our system, but by means of experimental data. Well, first of all, I will do a review of our structure. If you remember, this part in here, this inner part, is an angle control strategy. Okay, this is the set point, for example, for the pitch or for the roll angle, and this is the process variable, so the real value of this angle, of this pitch or your angles. Okay, we measure this, and this controller has not been tuned by us. This controller is by the manufacturer. So this controller is not of our interest. Okay, we admit that this controller has been perfectly tuned because this has been done by the manufacturer. So the aim of today's lecture is to find the model of all this set of elements in order to have a model that helps us to tune this controller, because this is the set point of the linear speed, let's say forward or side by side, and this is the real value. We measure this real value, we compare it with our reference, we get the control error, and then this control error must be manipulated by the mathematical law within this controller. This is the controller action of the linear speed controller. But at the same time, because it's a cascade control loop, the controller action of the outer loop, of the main loop, is the set point of the auxiliary or inner loop. That's our angle loop. So let's suppose that this V is Vx. This set point for the angle will be the pitch angle. So this will be the reference for the pitch. This will be the real value of the pitch. And the change of this angle will make the aircraft to go forward. That's the idea. If this angle is the roll, the roll angle, for example, then this speed will be the y speed. Okay, so side by side. Fine. So the aim of today's lecture is the following. We will give the system, we will excite the system with some experimental data, experimental signal. This signal will be introduced as a set point for the angle. This angle will be controlled. Remember, this by the manufacturer. And we will measure the output of this linear speed. So we will have this signal as an output signal of the system. As you can figure out, we will get the mathematical model of all these elements, of the set of all these elements. So if we try to model mathematically the relationship between this signal and this signal, we will have the model of the inner loop and the relationship between the angle and the linear speed, and also the sensor. That's the idea of today's lecture. And we will do this as a homework for all the angles and speeds of our aircraft. Okay? Important thing, here it says input and output signals. Obviously, the input is this and the output is this. But I'm going to show you afterwards that MATLAB, when you are dealing with the system identification toolbox, the graphs will show you the input signal and the output signal on the same figure. We will see it later. So remember about our architecture. We have the aircraft and we have the remote controller, the remote computer. So all the control strategies, all the commands and so on are within this computer. Okay? Here on the aircraft we have another computer, but here there is no control at all about this subject. Obviously here in this computer there is the inner control loop, so the angle control and the height control, because this aircraft will be flying at more or less a constant height from the floor. Okay? But here in this computer we will send the command and receive all the data about the navigation of the aircraft. I mean, the linear speeds, angular speeds, accelerations, height, battery charge, and so on. So remember, we have the pictures and the navigation data that are going from the aircraft to the remote computer, and then from the remote computer to the aircraft we have the takeoff and land commands, and obviously the set points for the angles. The software architecture is as follows. We will do everything in MATLAB. The reason to do that, remember, is because MATLAB is so familiar to us. Okay? If we change into C or Python, all the functions can become so complicated. But MATLAB is a high-level language with no need to be compiled because it's an interpreted language. So it's so easy for us because we know how to code more or less in MATLAB. We know how to use Simulink and so on. So it's so familiar to us. That's why I have chosen this software tool. Then MATLAB sends and receives all the commands from the robot operating system. This robot operating system is in continuous communication with the operating system that is our Linux, is a Ubuntu, okay? And then we have as a hardware the computer and the parrot with a Wi-Fi connection both. What's the main function that I have built in MATLAB in order to get the identification data? Well, first of all, I clear the command window, and then I clear all variables in order to have my workspace empty, strictly empty of variables. Well, I have an instrumental variable that it's drone ready that will be useful for us in the future. But today you can forget about this. The important thing is that in order to avoid, because this is an internal function, this is not formal. So that's why I'm using global variables. Be careful with global variables, because as you may know, a global variable can be modified by any function that is working in our process. Okay, so be careful with global variables. But for me, because it's an internal function that will not be used by anyone else than me, so I have used the straight path that it's, well, global variables, and forget about this. The global variables are the following. The subscriptions, you remember the ROS operating system has publishers and subscriptors. My computer subscribes to the image because the aircraft sends the image, publishes the images, and then my computer is subscribed to this item, okay, to this node. Well, then I have the navigation data because the aircraft publishes the navigation data and my remote computer is subscribed. Then what is my computer publishing? As you can see here, the commands for all the linear velocities, the commands for all the speeds. That's the idea. Then I have the geometry message. I will talk you about this later on. The input metrics is the input signal that I'm gonna send to the device, to the aircraft, and navigation, that is a variable when I'm gonna record all the nav data which I am subscribed to. First of all, which signal are we going to send to the system? A multi-sign signal. As the name says, a multi-sign, or as you may know, a multi-sign signal is a signal that is composed with multiple sign. Well, to be more precise, it's a multiple cosine function. Okay, but at the end, it's the name. It's a multi-sign. But I have built a multi-cosine function. Okay, I will explain you later on why, the whys and hows of this signal. First of all, I need to decide all the frequencies. These frequencies, as you can see here, the F, these frequencies are in hertz. As you can see here, it goes from 0.2 hertz, so a period of 5 seconds, and then the increasing in these units. So the array will be 0.2, 0.4, 0.6, 0.8, and so on, because the increment is 0.2 until 20 hertz. The sample time will be 10 milliseconds, as you can see here. Then the lowest value of this multi-sign, because I have a highest value and the lowest value, and the multi-sign will be between these limits. So the maximum value is 0.2. This is the maximum, as you remember, the maximum set point for the angle. This is the set point of the angle. This angle can go, this set point, from 0 to 1. That's the important thing. So it's not in degrees, in radians, it's normalized between 0 and 1. So I have chosen 0.2. As you will see later, in order to the aircraft not to move so fast all along or all across the laboratory. Okay? Then this is the number of periods of my multisign signal. So if the lowest frequency is 0.2 hertz, so the period for all the signal is 5 seconds, I have prepared an exercise, an experiment of 100 seconds, because it's 5 seconds multiplied by 20 periods. But as you will see, there is no need to have an experiment of 100 seconds. I will show you later. Then, with all these parameters for the multisign signal, I have prepared a function that generates this multisign. And it's not so immediate, it's not so simple, you will see later. This function has been built by me, you will see, but so this function doesn't come with MATLAB by default, and this function needs as input arguments the frequency array, the sample time, the number of periods, the lowest value of the signal, the highest value, and the angle that will be excited. Remember, these values are the set points of the inner loop, of the angle loop. And you must tell the generator which angle will be excited. So this can be pitch, roll, or yaw. What about this input signal? Why it is a multisign signal, as you can see here in the figure as an example? Well, it's because the multisign signal, first of all, it has a lot of properties that are so interesting to us. First of all, it's a dynamic signal. As you can see, this signal is moving from different levels, from different amplitude levels, all along the time. So it's very important. In opposition to a step function that has only this change, this is a dynamic signal. And it's so interesting for us because the identification procedure will be better if the input signal is so dynamic, because it will excite different frequency ranges of our system. As you can see here we have a very frequent signal, but as you can see here, we have like a square signal. Okay, it's an approximation, I know, but can you see here that the signal is not so frequent, and here is so frequent, and here it goes back to this. Here the signal is repeating, as you can see. Okay, because we have 20 periods. I have plotted only 1 period and a quarter of the following one. Okay, but this multisign signal, it's so dynamic, but it cannot be generated so easy. You must do the following. You must minimize the crest factor. What is the crest factor? The crest factor is the quotient, the ratio between the peak value of the signal and the root mean square value. As you can see here, the infinite norm, so the maximum value of this signal, the maximum amplitude value, divided by the root mean square value. Okay, remember the addition of all the values, and then the root mean, the root of the mean value. Okay, so this factor is very important because this factor C is always greater than 1. But we want to minimize this value in order to what? In order to make this peak not so big in comparison with the root mean square value. Why? Because the root mean square value, it's like a measure of the energy of the signal. Okay, so root mean square value is about the energy, the mean energy of this signal. So how energetic is this signal? And it's so important to excite the system with an energetic signal in order to make the system to move, okay? To have a rich output signal. That's our aim. And the peak value is the maximum value of the signal. So we want that the peak value not to be so high in comparison with the root mean square. So if the root mean square for a signal is this, as you can see, the peak value, taking this as a reference, okay? This is our zero. I know that the zero is here, but forget about this. This is our zero. If the root mean square value is this, and the peak is this, as you can see, the quotient between this amplitude in here and this root mean square is greater than 1. But we want this root mean square value, this energetic equivalent value for this signal, to be as close as possible as the highest value. That's our idea, because then we can say that for this amplitude of the signal, we have sent as much energy as we could to the system. That's the idea. So that's why we want this crest factor as low as possible. We want this, we know it's bigger than 1, but we want this value as small as possible. I will show you later on how it works, how MATLAB does this thing. Okay, it's about a minimization criteria. Well, the reference that I have used for this aim are here at the bottom of the page. The main one is quite old, as you can see here, but this is so interesting. Is a very celebrated contribution because it talks directly about the peak factor, the crest factor minimization using an algorithm. MATLAB has a function that is already implemented that uses this swapping algorithm in order to make the signal with a crest factor as low as possible. Okay, that's the idea. I will show you later. It's so interesting this, because if you don't do that, you can get signals, multi-sign signals of this kind. A big peak, and then the signal so frequent in here. Then a big peak, and a signal so frequent in here. And that's not interesting to us, because the root mean square value is so low. So you have used a big amplitude, a lot of different values, okay? But the energy is so low. So that's why you need a kind of signal like this with the root mean square as high as possible. That's the idea. Okay, so what about the generator? I remind you that I need the frequency array, so all the frequencies for all the harmonics within this multi-sign function, then the sample time, the number of periods, the minimum value, the maximum value, and the action. Remember, if the action is pitch, roll, yaw, well, gas, I'm not changing the height, okay, of the aircraft, okay, the height the Z where it's flying. So forget about this. We will not do experiments about this, but I have prepared the file for if you want to experiment with this, but it's not of our interest now at this moment. Okay, so well, first of all, I'm fixing all the issues about the amplitudes. As you can see here, I make the difference between the maximum and the minimum values. If I divide this difference by 2, I have the real amplitude. Remember, the amplitude is not this. It's not from peak to peak. It's from the mean value to the peak. This is the amplitude. Okay, so that's why am I doing this. Then, well, I normalize several things, but I want you to pay attention to this multi-sign clip algorithm. This multi-sign clip, well, I have modified the original function. That's the reason of these two. But this msyn clip is about this reference. So it's about the peak factor minimization. You will see it later. So this function is in charge to do the algorithm, because for given harmonics and given amplitudes and given sample time, you will see that this function will generate the multi-sign. Here I'm only dealing with the results and nothing to do on this, because I will give you this experimental data, well, this signal, in order to excite the system. And finally, I save the resulting data into a file called input data. Then what about the ROS commands for the aircraft? Well, first of all, I deal with the camera. Now for these experiments, I will not use the images from the drone, because I will not do the image recognition. We will do it later on in a week, okay? That's we're not interested in this at the moment, okay? But these commands are for the camera. As you can see here, I set the front camera, and then I toggle the camera in order to use the bottom camera, the zenithal. But well, now for this moment you can forget about this, because today we're not dealing with the image processing. Then, first of all, this is so interesting, because here I have the empty message generation. This in here, this message in the ROS environment is in order to give, for the standard messages, an empty message that will be used later on in order to make the aircraft to take off or to land, you will see, or to, for example, reset the drone if something weird happens. And finally, here for the message generation, as you can see here, I tell that the geometry message will be a 3 array. What about the publications? These are the publications from my computer, the remote computer, to the aircraft. As you can see here, I have several publishers. First of all, this is in order to reset the drone. This is for the magnetometer. This is in order to make the drone to land. This to take off. And this is to tell the drone all the set points for the velocities. So it will be the angle set points in order to make the speeds of the drone to change. So that's the aim of this publisher at the end. And then my computer is subscribed to the following: to the navigation data, as you can see here, and then to all the video streaming, the images sent by the drone. Obviously, today we forget about this, but this is very line numbers of my file. First of all, this here tells the drone, I'm only explaining you this. I will give you this function, okay? So you're not expected to code this. It's only for explaining what is the file doing, because it's not so immediate. First of all, this message tells the drone that the velocities that I will send to him will be given in three parts for the linear and three parts for the angular. So that's why I give this message. I send this message. This message tells that the linear speed will be given in these three components, and the angular speeds also with these components. Okay, that's the idea. Then I send this geometry message that I have generated here, and obviously with all these speeds. So first of all, I tell the drone speed equal to 0. All the speeds equal to 0. Then here I prepare for the receiving of nav data. Well, at the end, I ask the drone to receive all the nav data which I'm subscribed to. And then I get the first navigation data. Then I tell the drone, as you can see here, to take off. Remember the empty message that I have generated previously. Here, the empty message, you remember? Now I send this empty message because the takeoff does not need any argument. It's only takeoff. So I send the takeoff command to my aircraft, and the aircraft, as you will see later, starts to take off, and I wait for the hovering. Everyone knows what hovering means? Yes? So it means that the aircraft will be static but flying at a constant height, will be held in the air but not moving. Okay, so we'll stand static, okay, in the air. So I will know that the aircraft is hovering because I have, for the navigation data that I have received previously, okay, obviously here when I ask for the navigation data, the aircraft is on the floor, okay, but now the aircraft will be flying, will be hovering, or close to be hovering. So this state will tell us what's the state of the aircraft. If it's landed, if it's hovering, if it's moving, or similar. And this state will have a value of number 4 when it's hovering. So 4, state equal to 4 means hovering. So not landed, not moving, only hovering. So that's why I wait while nav data state is not equal to 4. Remember, in C, not is this. In MATLAB, not is this. Okay? And this symbol can be obtained with Alt, it's Alt plus 126, because this is the ASCII code for this symbol. Okay? So that means not. If I say not equal to 4. So while the aircraft is not equal to hovering, so the state is not equal to 4, I receive the nav data, and in order to not to collapse the microprocessor, I wait half a second, as you can see here. I wait half a second in order not to ask continuously for the navigation data, because this would collapse the system. Okay, that's why I wait. It doesn't matter, because here I'm only waiting for hovering. So here the aircraft is not moving at all. Okay, that's the idea. So this loop is only to make sure that the aircraft is prepared to start the experiment. So that's why I wait for the user to click a button. Here, I will show you later on, okay? But here, I'm waiting for the user. This UI wait waits for the user. Waits for the user to do something. And now is this, a message box that it's waiting for the, well, this is the message waiting for the user. The R drone is hovering, okay? I will show you later on. Then here I prepare the navigation array with an array full of zeros with 15 positions, because as you will see, I will record 15 data: the speed, the linear speed on X, Y, and Z, then the angulars, then the accelerations, the battery charge, the speed of the motors. You will see later here in the timer, okay? Well, then I define a timer. This timer is built in order to make all the experiment with a constant fixed rate, with a constant sample time. As you can see here, this timer, this function, is called timer function, okay? Then the M file that will do this timer will be called rtimer.m, okay? And then the period will be sample time that I have defined previously, 0.01, so 10 milliseconds. And this timer will be executed with a fixed rate at a constant time period. That's the idea. Then I ask for the user to press the enter key to start. That's the need of this. That's why I have these two commands. Then I wait in order not to collapse the system, and then I start the timer. And here the experiment begins. I will show you later. Then I show the message, press enter to stop, and I wait the user in order to press the enter key. If the user presses the enter key, the experiment stops. So that's why I stop the timer, I delete the timer, I wait half a second in order not to collapse the system, and then I tell the drone, well, you can land. That's the idea. So in order to see how it works physically, what can you see in the lab is this. I have recorded a video. Well, I went yesterday to the lab and I recorded this video, this small video, in order to show you, well, this is the ground floor lab. That's where lab sessions will take place, okay? And, well, this is the drone that you will have the data, because that's the data I have collected yesterday, okay? So let's have a look at this video. As you can see here, the drone is landed. Then I send the takeoff command, okay? And here, the drone, as you can see here, first of all, it takes off, but it's not on hovering. Now it's on hovering, and then I press the enter key in order to start the experiment. And here you can see that the robot, the aircraft, is reacting to this multi-sign signal that we have as an input, okay? As you can see, it's like balancing, okay? Well, I have recorded this video in order to show you so close that the drone is balancing. Here is another perspective. Now it's hovering, and then it starts the experiment, as you can see. First, the multi-sign. As you can see, it's going forward here. Here, at the beginning, it's going forward so fast. If you remember the multi-sign, first of all, the highest value lasts some long time. That's why, first of all, it's going forward so long. That's the idea. And then it's going backward. And then here we have the high frequency values. As you can see, the drone is balancing. So this is what you can see when you're sending a multi-sign signal to the aircraft. So, which transfer functions are we expected to find? First of all, the relationship between the linear speed in the front axis with the pitch angle, the roll angle, and the side speed, the Y speed, okay? And then we will change the yaw, and we will see what about the angular speed of the aircraft. Because in order to follow the line, the straight line, if we have the aircraft not in the good direction, if we have this direction, that it's not the good direction, we need to do this movement. So we need to go forward, but at the same time to turn the aircraft. So that's why we need also this. Not only the forward or the side movement, but also how to turn the aircraft. That's the idea, okay? Well, we're gonna use, now I'm gonna show you, when I have all the data that has been collected in my computer, I will use the system identification toolbox in MATLAB, okay? As you can see here from the command window, I type the system identification, and then a graphical user interface opens. I will import the data, time the main data, and this input value, remember, pitch input in here, okay, pitch input. So I will type pitch input, okay? Then, what about the output? Is VX. Be careful because it's case sensitive, okay? Fine. Then the data name will be my data. Okay, it will be demo session, for example, okay? Starting time will be 0 because the experiment starts at 0 seconds. And the sample time is, remember, 0.01. Remember, 10 milliseconds, okay? I import, and then, as you can see here, I have the data loaded, okay? Fine. Now, the important thing is that first I need to pre-process this data. First of all, I have an experiment. You can plot this experiment, time plot, in here. And it appears, can you see the input and the output? Remember that I told you before that MATLAB shows input and output signals here as a title. So this is the signal that I have used for the presentation, input, output. And can you see that I have 2 periods and a half? Because here, the reaction, is it clear that is 2 periods and a half? It's the third period is not full, okay? Fine. So this is our experiment. I will split this data into 2 different sets. First of all, the identification data that will be used on the procedure, and then the validation. So this will be for the adjustment of the model, and this will be used for the validation of the model, okay? So let's say, for example, that for 5 seconds, remember that the first frequency or harmonic was 0.2 hertz, 5 seconds. That's why the multi-sign lasts, the period of the multi-sign is 5 seconds. So I will use 5 seconds for the identification and 5 seconds for the validation of the model. So I will take this data to here. It was already here, but I'm showing you how to proceed. Then here is the working data. I will select the range, okay? Select the range. That means that this data can be split into different sets. First of all, from 0 to 5 seconds, can you see here? From 0 to 5 seconds, I will use this data, and the name will be adjust data. So here, a new data set has been generated, can you see here? And it's adjust. Now, from 5 to 10, for example, I will use the validation data. Obviously, the adjust data will be used for the model generation, and the validation will be used in order to check that the model is fine. Okay, that's the idea. So I insert this. Now I have the adjust and the validation, and you can see that this representation is so different. Okay, fine. Now I close this, well, close or the cross, anything. And now I need to put the adjust in here, okay, and I will remove the mean value. Why do I do this removement of the mean? Because a transfer function has nothing to do on the offset of a signal, on the offset difference between the input and the output signals, okay? So the transfer function is a gain, is a dynamic and also a static gain. So it's a relationship between the output and the input as a quotient, as a ratio of polynomials, okay? But nothing about an addition of offsets, okay? The transfer function is a quotient, not an addition. So that's why I remove all the means for the input and the output signals, because I don't want nothing about an offset difference between both signals, okay? So I have done this with the adjust. Now I need to do the same thing with the validation. So I remove the mean for the validation, okay? Fine. So now I will drag and drop the adjust signal, but can you see that now it has a final D, an ending D? This is because I have removed the mean value. The adjust is the original value, but the adjust D is with the mean removed, okay? That has been removed. Now, with this data, I can estimate a model. Let's say a transfer function model. Can you see here? So a new window opens, and this transfer function, you can specify the number of poles and the number of zeros. So the degree of the denominator and the degree of the numerator polynomial. Let's say 1 and 1. Sorry, I'm only checking. Now it's for checking. Okay, let's say the simplest model. Well, the simplest is this: 0 and 1. Okay. Now you can press the estimate button, and the process starts. As you can see here, some kind of algorithm is being applied. Here it says a nonlinear least squares algorithm. Okay, a least squares algorithm is quite similar as when you approximate when you have some scatter plot, when you have several data and you want to approximate this into a line, okay, a first order polynomial, okay, you use the mean squares method, okay, the least squares method. So this is like an approximation of this method, okay, but it uses like a dynamic parameter that improves the solution, improves the model, minimizes the error between the model response and the real data by means of an iterative process. Okay, that's the idea. Okay. Finally, here is very important, these two numbers. The fit, can you see that it's 46.42%? So it seems that it's not quite good. I hope it would be, I wish it would be 100%, okay? And this final prediction error that I encourage you to do a web search for this final prediction error, it has something to do with the Akaike information criteria. I encourage you, I invite you to do a web search about this number. This number should be as small as possible, okay, this FPE. And it's very important because this number, just before this number is important because it takes into account the minimization of the error. So how small is the error? And also, how big is the model? So this number puts into your knowledge that if the model is so big, it's not enough good to have a good approximation. Because if you put a model of order 1000, obviously this model will work. But you cannot deal with a model of 1000 other polynomials. Okay? So that's the idea of this final prediction error. This number considers also the minimization of the error, so the difference between the real data and the model output, and also how big is the model, because your interest is to have a good approximation, but with the minimum model order as possible. That's the idea. So this number is so interesting, but it's more interesting the FPE, okay? Well, now that we have a model, as you will see here, now we have the transfer function number 1. This is the model. And then you can use the validation data. Can you see here the validation data? In order to be used as a validation data for this model. Can you see validation data? It's different from the working data. And now, if you click on the model output, you will see the difference between both outputs. We click here. And as you can see, the model, well, the original signal is in black. That's the original signal. And the model is this signal in blue. As you can see, the approximation is not quite good, okay? It's not good because this peak is so significant, as you can see, but it's not achieved by the model, okay? So this model is not good. I will take this model and throw this model to the trash, okay? If you double click here, you have everything that you have thrown to the trash, okay? Fine. You can empty at any moment, and the trash is empty. So again, let's estimate another model. Let's say now, I don't know, 3 and 1, for example. That's your work. That's the work I expect from you. I will give you the data and do this process by your own, okay? Is it clear? That's the idea. Fine. So I estimate, as you can see here, the final prediction has decreased significantly, okay? And obviously the fit, now it's double the fit that we achieved before, okay? So it seems that this model is quite good. Okay, let's check. Again, I have the validation data, remember? So now I click on the model output. And now, well, it's better, as you can see, okay? Here, but this could be like noise. Well, I don't know. It seems that this model is so good. Now you can see that the fit now is 64, not 84 like before, because now you're using the validation data, Okay, here when we were using the model, here for this model, this fit here 84 was because we were using the adjustment data. Okay, and if you compare the output with the adjustment data, obviously the fit is so high. Why? Because you're comparing with those data that you have used for the adjustment. Okay, but when you used a different set of data, the model fit worsens. Okay, well, so let's now check another model. Okay, transfer function model again. Let's say, I don't know, 4 and 3. Obviously, I know the best model. Okay, I'm only acting. Okay. Okay, here we have another one. As you can see, the final prediction error is smaller than before. The fit is slightly higher than before. Okay, remember, well, before it was 84, now it's 87. Let's check. Transfer function 2. If you want to compare both to the output here, can you see that now the fit is 71? Okay, dot 74. It's greater. Now you can see that here maybe it's a bit confusing because both are on green. Okay, can you see? But the light green is for the transfer function that I used before, and now can you see here that the fit with the dark green is better? Okay, that's why we have a 71. If you want to see only the last model, here it's clearer. If you want both, okay, here. If you want no one, you have only the original data, one model, another model, whatever you want. Okay, so the message for you is that you will be expected to do this procedure for all the transfer functions. Okay, for the pitch, for the roll, and for the yaw, for Vx, Vy, and the angular speed, the rotational speed. Okay, you will see that you can try different models. Let's say now, I don't know, 5 and 3, and we can estimate. Now it's more or less, as you can see, it's more or less the previous values. Okay, and the approximation is quite good to the validation data, but it's more or less the same fit. So as you can see, I have increased the model order, but the approximation is not better. That's why this value, this FP, has increased a bit. Remember, 170 something, and now it's 180 something. This has worsened because I have increased the model order, but the approximation is not better enough. Okay, that's the message, the final message I wanted to send you for this for today's lecture.